Imagine that I'm standing here holding the end of a rope. So I'm over here on the left end, and while holding the rope, I rapidly move my hand up, down, and back to the starting position. If we were to take a snapshot of the rope immediately after I finish my motion, we're going to see something like this. The rope has a squiggly disturbance that mirrors the motion I made with my hand, up, down, and back to the middle. And the rest of the rope is still flat. You might have seen something like this if you ever play with a jump rope and wiggled it back and forth, or a slinky and you've seen that wave back and forth on the ground, or if you've been in the gym and seen somebody doing exercises with large battle ropes, slamming them up and down repeatedly. And we know over time, this disturbance is actually going to make its way through the rope. If this is what we observe right after my hand motion, at some later point in time, we will observe that the beginning of the rope is back to its original shape. This squiggly disturbance has made its way further down the rope, and it will keep traveling in this direction until it reaches the end of the rope. This is exactly what a wave is in physics. A wave is a disturbance, in this case, the squiggle in the rope caused by my hand motion, and that disturbance can propagate. It can travel or move in a particular direction. So, a wave is a disturbance that can propagate. This particular example is called a mechanical wave. It's called mechanical wave because the disturbance is traveling through a medium, in this case the rope. So mechanical waves travel through a medium. One important point about waves that is worth noting right now is that waves transfer energy without transferring matter. So what that means is that the disturbance that is moving here, the squiggly shape, is moving through the rope, but it isn't moving the rope to a different position. Any part of the rope might go up and down as the wave travels through that section of the rope, but the rope itself is not going anywhere. Rather, it's the kinetic energy imparted to the rope by my hand that is transferring from particle to particle and making its way through the rope. So, waves transfer energy, but not matter. So in my first example, I only jerked my hand up and down once, which created a single wave pulse that moved through my rope. If instead I were to keep moving my hand up and down consistently, I would see a waveform that looks something like this. And when we model a wave, there are a few key characteristics that we need to know about that wave. First is the period. Period is measured in seconds, and it tells us how long it takes for one wave cycle to complete. Next is the wavelength. Measured in units of distance, like meters, the wavelength is the distance between identical points of adjacent waves. And finally, there's the frequency. So if the waveform that we've drawn here takes 1 second, there are 4 cycles in that 1 second. That means it has a frequency of 4 hertz, or 4 cycles per second. So the frequency, measured in cycles per second, tells us how many wave cycles there are every second. Now, using just these basic anatomical properties of a wave, we can start to figure out more interesting physical characteristics, like speed or distance over time. If we want to know how fast a wave is traveling, we can take its wavelength, which is the distance covered by a single cycle, and multiply that by the frequency, which is how many cycles are completed in a second, a given amount of time. The cycles cancel out, we're left with units of distance over time, the same as speed. And that's our equation for the speed of a wave, wavelength times frequency. The standard units for speed are meters per second. There are a couple factors that affect the speed of a wave. The first is the wave type. So different types of waves move at different speeds. And a relatable example of different waves moving at different speeds is lightning. Have you ever seen lightning strike or been in a thunderstorm? You know that the first thing you see is the flash of lightning, and then you hear the thunder associated with that lightning flash. So the lightning comes first, and the thunder comes second. That's because those are two different waves that are part of the same phenomenon. When the lightning strike hits, you see the flash first because that's an electromagnetic wave, light. It travels much faster than the sound associated with a lightning strike. Electromagnetic waves are special because not only do they travel very fast, they also don't need a medium to travel through. The thunder, on the other hand, is a sound wave, traveling slower than the light. So you'll see the lightning before you hear the thunder. Different wave types move at different speeds. The second key factor that can affect the speed of a wave is the medium through which the wave travels. And we'll look at sound as an example here. So when someone is talking, right, we have this talking head using their vocals, they're creating some vibrations of the particles in front of their mouth. That's the sound wave. It's the vibration of those particles propagating through the air. When you speak, your vocal cords are exerting force on the particles just in front of you. Those particles vibrate back and forth, creating a compression that transfers to the surrounding particles. As the vibrations continue to propagate, the sound travels. You can imagine that if these particles are packed closer together, those vibrations are going to transfer a lot more quickly because the particles are colliding faster than if they were further apart. So sound travels faster in water, a liquid, than it does in air. For exactly that reason, the particles in the liquid are closer together. As the particles are closer compacted, they collide more, and the propagation of the wave happens faster. So, different waves move at different speeds, and the medium through which a wave travels can also affect the speed of a wave. Okay, so let's try to summarize all this information. We have waves. A wave, a disturbance that can propagate, has a few key characteristics. There's the period, or how long it takes one cycle to complete. There's the wavelength, or the distance between identical points on two waves that are next to each other. And the frequency, which is how many wave cycles complete in one cycle. In this case, we have 2 cycles in 1 second for a frequency of 2 Hz. Wave speed is found by multiplying wavelength and frequency, and wave speed is affected by the type of wave and the medium through which the wave travels. Mechanical waves are waves that travel through a medium, so sound, the example of a slinky or a rope, ocean waves. And electromagnetic waves, like light, are special because they can travel through a vacuum. They don't have to have a medium in order to propagate. But all waves, no matter what type, transfer energy, not matter.